Hello everyone, I hope you are doing great. Uh, Today I'm here to talking with you about simulation of solar cell with COMSOL software. Um, Here I've installed the latest version of COMSOL Multiphysics of 2023, COMSOL uh, 6.1. Okay. uh, Here, the overview of the first panel of this software. Uh, as you can see, we have a new panel that allow us to choose option. For example, wizard model, blank model, or something else that we can open the file with this button. Here I use the blank model that show this panel. As you can see, there is no any object here, and we must to produce and define the geometry and related physics, and also mesh and study that I explain you later. Okay, here at the first I must define the component. As you can see, we have uh, uh, six option, six option. 3D, 2D axisymmetric, 2D, 1D axisymmetric, 1D, and uh, zero dimension or without dimension. Um, okay. In this tutorial, I want to use a 1D example, but in the later tutorial, I will show how we can how we will simulate 2D axisymmetric or 3D solar cell. For example, Perovskite solar cell and CIGS solar cell or CZTS and something else. Okay, here I use 1D component. Okay, uh, in this geometry I can click, use the right click, and you can see these options. I use interval. From this interval I must input the coordinates, first and end coordinate for the thickness of the layers. Okay, for example, I use I can simulate a perovskite solar cell. Let's assume that, let me show you in the paint. Okay, here we can assume we have this solar cell with this structure. Here ETL layer or electron transport layer, uh, that can be uh, choose materials such as TiO2 or SnO2 or something else. Our perovskite, middle of this sandwich between ATL or and HTL, whole transport layer. That whole transport layer can be choose materials such as PCBM or spirometallurgy or Cu2O Okay, here we can choose a conventional perovskite MA PBI3. We have two contacts. Here we can choose gold contact or AU as a symbol. Okay. Here in this front, we have maybe we have fluorine tin oxide or FTO. Okay. The light comes from the top of the cell. Uh, and here we want to introduce this layer to our geometry. We want to use abbreviation of ETL, perovskite MAPBI3 or PVK, and also for HTL Spiro. It's a conventional HTL in Perovskite Solar Cell as HTL and AU or something else. In one dimensional, we don't need to define the AU or gold and FTO, as we want to define them as contacts. Okay, let me write that contact. This is it can be a front contact, F contact, front contact, and AU as B contact, back contact. Here in one dimensional, these two contacts will show as a point in the geometry. Okay. I can use the two coordinates 0 to thickness ETL. Okay. Here, as you work with COMSOL, in the global definition, I can define the value of ETL thickness. For example, 50 nanometer. We must input the units of the parameters in the bracket, as you can see. Okay. Also, let me copy that and paste. HTL, for example, 200 nanometer. Be careful about the capital words and don't use a capital for thickness or something else. Okay, and also thickness PVK as perovskite thickness. Here I assume 400 nanometers perovskite. Okay. The coordinate first, 0 thickness ETL. Let me select it. Okay. As you can see here, also before working with the geometry, I can use the unit lengths for easy definition. I can use a nanometer and I use the zoom to selection here, and also zoom extent to see what I created. Okay, as you can see, this layer was built from 0 to 50 nanometer. Okay, I can duplicate this layer. Let me do that. Okay. Okay, the middle layer here, perovskite layer, must be defined from this point to end point. The initial point is the thickness of ETL. I must add the thickness of ETL to the first point. Let me do this by plus thickness of ETL. Okay, from 0 plus thickness ETL to thickness PVK, and I will select it, and I'll choose zoom extent. Okay, look at this. From 50 nanometers to by right clicking and using the touchpad, I can move this geometry to anywhere that I want. Okay, from 50 nanometer to 400 nanometer. As you can see, we define the perovskite 400 nanometer, and we expected that this point must be in the 450 nanometer. Okay, but here this is to 400 nanometer drawn. It's because of the second coordinate. We must add the first coordinate plus last coordinate. Okay, as you can see, this geometry it's okay now. It's 450 nanometer. Okay, let me duplicate that. Okay. As I introduced and explained before, we must let me do this 0 to this endpoint to be a regular formation of introducing. Okay, I can use this 0 plus thickness ETL, thickness PVK, plus thickness of HTL to plot this object. Okay, as you can see, the geometry was built up, and from 0 to 50 nanometer, let me zoom on it. We have the ETL layer, and from 50 nanometer to 450 nanometer, we have perovskite layer, and from 450 nanometer to 850, we have excuse me, we must choose HTL. Excuse me for that. Okay, now we have this a structure that built in the 600 uh, 550 nanometer. It showed that the thickness of HTL is 200 nanometer as we defined in the parameters. Okay. Okay, for simulation of solar cell, we need to define a physics. The related physics can be choose by a semiconductor equation or writing some codes by adding mathematical module that I will introduce in uh, later tutorial videos. But now I use um, simple and ready physics for simulating the IV curve of the solar cell. Let's do it. Add physics from this button. I use a semiconductor. We have three options: semiconductor as a conventional physics, or Schrödinger equation, or Schrödinger-Poisson equation. These two options is for considering the material as the uh, quantumic behavior, but we want to solve the classical mathematical for the our structure. As you see, our thickness is above the 10 nanometers that guarantee and assure us to use classical equations. Okay, I choose the semiconductor semi by double clicking, left click 2 times, multiple. Okay, for the start I can right click on semiconductor. I choose group by space dimension. By this work uh, the related equation will be separated by domains and boundaries, and it can help us to introduce uh, correctly the layers with the related properties. Okay, as you can see, I can choose a semiconductor by equation. As you can see, a study equation, it can be a study controlled. You don't see anything here. It's because of the study. When the study controlled, I must choose a study uh, from this button, and when the study is introduced and defined here, the equation may be changed. Okay, here I can use the other option, stationary, time dependent. For example, I use a stationary. Okay, when I use the stationary, the final equation will be shown. This is Poisson equation for the uh, carrier density, and we can see the gradient of the relative permittivity and the gradient of divergence of the gradient of electric potential here. Okay, I can use the reference temperature. The reference temperature in the COMSOL is defined 293.15 Kelvin. Maybe it's better to be 298, as we want to consider the 25 degree of Celsius, the condition of this illumination of light in AM 1.5 point global. I can use I can introduce all of this parameter, all of this physics behind of this data in other tutorials. If you want, please leave a comment for me, and I will build videos for you about that. Okay. Here I must choose a cross-section area by introducing that as a area with unit of a square meter. Let me introduce that as a area. Okay, and I define this parameter here. Please be careful about what the sentence you use, what the words you use. They must be exactly as the introduced in the related reference. Okay. As you can see, it's shown in black color. When I choose mistake or wrong notation, for example, area 0, you can see this text will be shown as a yellow color that tell us this is let me show you unknown variable area 0. When I correct it, you can click other area, and you see the this button, these parameters will shown on black color. That guarantee you input that right as a right value. Okay, in the model properties, the carrier statistics can be chosen by two options: Maxwell-Boltzmann and Fermi-Dirac. This is related to your structure, what the structure you used. For example, in Perovskite Solar Cell, the Fermi-Dirac statics, it's a good approximation for the simulation of the solar cell. I can also talk about these two options in the later videos, but now let me choose Fermi-Dirac, and the solution is can be chosen for electron and holes or majority carriers. And the majority carriers, it's the approximation that not solve for all of the carriers. Okay, just majority, not minority carrier. Let me choose electron holes. Okay. Optimal averaging for the diffusion enhancement factors. The COMSOL algorithm use the GNGP. Let me show you in the following that can choose the equation with the optimal way of the solution. I unbox it and I don't use here. The interface continuation parameter is here as shown 1, and we don't use no continuation in this example. Okay, as you can see, finite volume or other ways can be chosen for the approximation of simulation. Okay. For the other parameters, I can use semiconductor material. For example, here equation will solve for the all of the layer that I choose in the basic or main the equation. I choose all of this layer. In the semiconductor materials, I can see the all of equation. Here rho is a carrier density, or all of carrier density that can be evaluated by Q, electron charge, multiple P minus N plus ND plus minus NA minus. Pn are the hole and electron density. Nd plus are the ionized donor density. It's related to n-type semiconductor, and R minus it's related to acceptor density of the semiconductor material. It's related to p-type semiconductor material. Let me choose the correct this value to 298 Kelvin. Okay. The material properties for solving this equation are the relative permittivity, band gap, electron affinity, effective density of S states for valence and conduction band that can be chosen from material. From the materials, I can choose the blank material and the sprang material. Okay. I can choose each of materials separately. For example, I choose this material as HTL, and also I click just on the related geometry. As we know, this geometry is related to HTL. Okay. I choose another blind material and I click on the middle of this geometry that's related to PVK, perovskite. Okay. And another material, ETL. Okay. And I click on this section of geometry. Okay. I must define all of these parameters, and we have many ways to calculate these parameters. For example, we can choose the DFT, molecular dynamics. We can choose the our experimental ways. Also, I will talk about it. For example, a space charge limited current, SCLC method, or Hall effect measurement method. Also in simulation by atomistic tool software by quantum sperso. But we have some limitation on the calculation. Also, we can choose good references from the Google Scholar, from the Scopus, from the ResearchGate, and other platform of other scientific platform for achieving to this data and using the valid data for the simulation. let me search about this data. Although you can search my name, and I work on this topics, and in in one of my recent research, for example, a comprehensive study of anomalous hysteresis behavior, uh, that published in scientific report, and I can choose this data. um, Also you can choose this data and reference to this paper. uh, this is a good paper about the anomalous hysteresis behavior in perovskite solar cell. It solved the old data in time dependent study. Okay, by a code, not COMSOL, but a code. But it can be simulated by COMSOL also. Okay, I uh, I use this data, for example. Okay, in this example, you can see the thickness 50 nanometer for TiO2, MAPBI 300 nanometer, and let me introduce the 300 nanometer for PVK, and 200 nanometer for Spiro HTL, 300 nanometer, 200 nanometer. Let me talk about it. Okay, as you can see, the thickness of ETL HTL layer was ever defined, 550 and 200 nanometer respectively. For perovskite MAPBI3 as conventional, 300 nanometer was chosen. Let me check out 550, 200 nanometer, 300. Okay. Uh, okay. For ETL, affinity was 4.1 electron volts. Band gap is set as 3 electron volts. Let's introduce that. Okay, for ETL, band gap was set 3 electron volt. For definition electron volt in COMSOL, use capital V, which show the electron volt. The electron affinity was choose 4.1 electron volt, capital V. Okay. The electric permittivity is set 31. Here I use 31. It is dimensionless, that don't need use the 1 in bracket, just leave it without any units. For effective density of a state, conduction and valence band, both of them are set as 1E20. Okay, 1E20, 1E20. Please careful about the unit. Here the unit of COMSOL is cubic meter, 1 per cubic meter, but here it's centimeter cubic, and we must to convert it to cubic meter or centimeter. I use centimeter here. Okay, I can also copy and paste that here. Okay. For electron and hole mobility, we said that 1e minus 2 or 0, 0, 1, 1e minus 2, the unit is a square centimeter per divided by volt multiplied second. Okay, for mu p, this value is 2. We can copy paste